Okay, so for this next section, now we're opening this up to comments and questions initially from panel members. So I invite the panel members to turn your cameras on. And if anybody has a question or a comment, then please unmute your microphone.
Well, I will start. Thanks, Michael.
Okay, very good. Hello, Marie.
Good afternoon, everybody. Actually, I didn't send anything as I wrote because I believe that you summarized properly in the document you sent the point. We discussed it to have as a main reference of the event. But actually, following the discussion, we have listened. I believe that I would like just to add something on my view on the problem. But basically, I believe that the concept was properly summarized by several talks already. I mean, I just pick up Tony, Silvestre, Soraya. Actually, the main issue about strength is what we are aiming at, in the sense that the target is fundamental, because I believe that we can identify at least three, in the sense that they provide support to the definition of criteria of data for design application. So in that direction, I believe that the task, I would say, is relatively easy, in the sense that, as you point out before, we need to define the design allowables. In that sense, a pragmatic way of doing that is, I would say, just a matter of definition, in the sense that as the activity devoted to the definition of standards, so you need to define correctly how you measure the quantity and which are the procedure for doing that. Then you have some data you can use with a specific scatter for design application for a specific part in a specific condition. Differently from the scientific point of view, I believe that the concept of strength is very difficult to be defined. And I would stay more on the point raised by some of the people who talked so far. I mean, the first one was Ramesh, but that is also my way of addressing the problem, is that it's much more better to stay on the definition of driving forces for different mechanisms, because failure can have, and also strength at the same time, can have a million of meanings, depending on which viewpoint you are considering, because and which mechanism you are activating, because it's enough to switch from tension to compression to change completely the scenario, from stochastic to I would say kinking, stochastic failure to kinking, and so on, even moving to transverse, as Federico was showing. We have different situations. So at our level, considering our community and the people, most of the people I'm reading through the list of participants are from academia or scientific level, I would say that in that case, the concept of strength, as was pointed out, is no meaning, I would say, because it's better to consider failure associated with some specific mechanism. Then moving to structure, as I remember Steve was speaking of that, I believe that at that level, strength is the result of a progressive evolution of damage. And at that point, the definition of a correct procedure to account for all the potential sequence of different mechanisms, which is synergically acting or not, is probably the best way to consider. That is basically the way. Possibly we can have maybe other situation I did not consider, but still I would say it depends much more on which level of scale we are considering. Originally, when we start thinking about this workshop, the idea was to stay in a more, say, closed environment, limited environment, remaining, I would say, at laminar level. And at that point, it's probably much easier to find a common definition. If we started to include, and that was probably the discussion we had already also by email, if we move from lamina to structure, there is a variety of situations which are moving from the basic mechanism, where I would say is relatively easy to identify what we are speaking about, to laminate and even structure where you have a combination of a sequence of events which is bringing you to something which is probably the inability. Failure is even at structural level probably not the correct definition, because probably failure is the inability of the structure to perform the function the structure is designed for. And we can even complicate the scenario if you move to fatigue, which is my main business, where
Let's stay off that one for now.
you can really define failure according to different concepts. If you want no cracks, no damage, stiffness loss, or separation. So I believe that just to getting back to the original point, the main issue we should, if you want to identify a direction, we should classify the level where we are working on. Thank you.
Okay, thank you very much. I'd now like to ask Tony Was. Tony, did you want to make a comment, question?
Yeah. Well, I think the speakers highlighted many different issues. I felt that the topic was unidirectional strength, but we ended up looking at transfers. We ended up looking at compressive strength, and we ended up looking at a variety of values. So, Michael, I don't know whether one of the things you said you wanted to achieve was to seek consensus on whether we can get the community to agree to a definition of strength that could be used for differing purposes, right? And Ole Thompson here has written a comment which suggests that maybe when we have to look at allowables, we should look at a way to unify. So he's suggesting that one of the things we may want to do is look at a structural property or with the recognition that this quantity will depend on a number of factors, right? But for people like engineers working in a company like, say, Airbus or Boeing, working with laminates, and boy, it's going to become even more important, right? I mean, there's plans to go into AFP structures. There's plans to have wings that have steered fibers, etc. So the design space is expanding, and structural designs, including not only the structural types we address, but even including discontinuous fiber composites, are expanding. Applications are expanding, and I think that it'll be a challenge to keep up, to deliver understanding and design tools that are useful. So from a pragmatic point of view, I think that the idea of measuring strength using a UD laminar, I think it's useful. It is useful. The question in my mind, which needs clarification, is that quantity. Let's say we agree that there is a quantity that we can get out of a test like that on a standardized test specimen, let's say. And then let us imagine that we have a way to explain through modeling what might happen if you deviate from the standard. Let's say you make it wider, this is what's expected. If you make it thicker, this is what's expected. If you can bound the results in that manner, and then also come up with strategies to extend it to laminates that are useful for airframers, laminates that are useful for setting up allowables, then I think we would have achieved a good purpose. Now, when you go to other situations like notched specimens, compression after impact that some people were talking about, the problem becomes much more complicated. You no longer have a good idea of how what you measured in the UD test translates to those types of structural tests. Those are actually structural tests, right? The way I look at it is they're not, you're moving away from a basic fundamental property that you can define and measure to something a little bit more complicated, because a lot of more other factors come into play in those situations. I think those are best addressed with good models, developing models that are based on those fundamental properties we measure. So the challenge to me, I think, is coming up with definitions at the simple coupon level that you suggested and Federico suggested, and asking a question: how can we use that to do structural component character? And I'm thinking selfishly a little bit from an aerospace point of view. So I'm thinking of, if I have the unidirectional strength, how can I use that to bound my responses for open hole, compression after impact, a stiffened panels that have cutouts or maybe impacted? How can I make that translation? How do I define the pathway to go from the unidirectional definition of Wisdom and Paris, take that as sort of the material characterization number or numbers? It should be a spread, really. It should be a mean plus some variation. Okay, how can I take that and bound my allowables for those structural components? To me, I think that's an important question that we need to address. Come up with some modeling strategies, etc. I don't know how to do it. I'm just throwing it out and saying that that's, I think, what we need to do as a community.
So I think you've raised quite a lot of issues there, important ones. And I think there's a key question is, what is it we want? What do we want to do with this strength value? Because is it just to get a fundamental value for comparing materials? Do we want to use it in design? Do we want to use it in predicting failure? And definition may depend a bit on what we want to do with it. I think this needs a bit more consideration. Clearly, we have to start somewhere. So we started with some fairly basic, and I think there's obviously going to be a lot of work still to do. You mentioned Ole, and I will ask him later to say something, perhaps if he wants to. But Stephen's had his hand up. Stephen, did you want to make?
Yes, I guess it was really just to build on Tony's comments and in part reply to him. I think for this discussion, we perhaps want to avoid definitions of structural strength and structural failure. What I was particularly trying to articulate in my slides was more about exactly what you were saying about how do we take a fundamental definition and move it up the length scale by whatever definition our failure at that scale is. So rather than trying to say, put any definition or restriction on what structural failure looks like, but to say, I think as we probably all agree, we need the tools and the mechanisms to move from the fundamentals at, I guess, the more academic end of the scale to the practical and more applied end in a seamless manner. And I believe it is through that mechanistic physics-based understanding rather than just a top-down measure, test, and create sort of design allowables, because as is common across all of the talks, if you change some very minor things between one test to another, you have to test all over again for a different material, a different length scale, a different size. So to really move things on, we need to be able to extrapolate, extend, and exploit the fundamentals. And this workshop is about, as academics, trying to get some agreement on those fundamentals so that we can push that out into the community and support the wider engineering community in how to deploy and apply that.
Thank you, Stephen. So, Ole, would you like to make a comment?
Can you hear me now?
Yes.
Well, it's I put a couple of provocative questions into the debate, and I've been following the conversations with a lot of interest, and of course it's incredibly tricky. And my provocative questions is not because I actually have the answer, obviously. So my own take on this, which I tried to promote, was that I'm not sure that we can really grasp this by coming from the material scale and move upwards. Because at the end of the day, what we are here to do, or what what this is about is, or what the objective must be, is to be able to predict when a structure, a structural system ceases to do its or perform to its purpose, so that it fails. And you can correct me if I'm wrong, but in most cases I know about and I can see around, the actual collapse of a structure is seldom directly because of a material scale level event. It's typically something that involves structural effects, very often some element of loss of stability, not just for compression loaded structures, which then leads to a nonlinear response, which then triggers, could be debonding or delamination because of very high interlaminar stresses. And these things are very often triggered by imperfection of geometric deviations that are not just on wrinkles in laminates, but actually on larger length scale because of mold tool defects, imperfections, and so on. So this means then that the material failure actually comes in as a secondary or second or third effect after actually the structure has lost its life already, or it's close to doing that. So maybe another approach, and I'm not quite sure I know how to do it, is can we come down from the structural response and use that using multi-scale models, which of course need some sort of input about material allowables, but use that as the basis instead. Because I'm seeing that we seem to be debating many of the same questions over and over again, and we are of course gaining some headway in it, but I'm not sure we really are grasping the essence of the problem. And I also see that the increasing number of material systems and architectures that we perceive to be composites that are also going into use now, it moves much faster than we are doing with our considerations of UD laminate. So again, sorry to be provocative, but I'm just throwing that into the debate. Are we posing the questions correctly? Thank you.
Thank you very much. Federico, did you want to respond to that or have some other question you'd like to raise?
Yes, well, it's very well connected with all the observations. In fact, originally we discussed about the possibility to consider just lamina, laminate, or other level. And we decided to open the discussion today and see what happened later. Going to this classification, I think that we can only apply the concept of strength to lamina and laminate as much. When talking about open hole, compression after impact, for not to mention complete fuselage panels, the concept of strength, at least for the designer, they are not interested. They are just interested in knowing if there is any type of damage or not for a certain applied load. Sometimes we have performed hundreds of tests for the aeronautical industry, and sometimes we have asked them, can I take the specimen till the final failure? And they say, I'm not interested, but if you want to do it, you can do it for you. So the work for me, the world strength should be applied at laminar level. And for me, what is our main concern should be how this information can be used for a designer at the level of a laminate to predict the behavior of a laminate without having to test all type of laminate under all type of loading and all type of temperature, humidity, etc. And of course, to help people with this information, designing a structure. That's all.
Okay, thank you. Other comments or questions from the panel?
Yes, Michael, I perhaps want to raise a point from my perspective. I probably, as one of the few panelists here, I am raised as a material scientist, and I think most people here have more a mechanical or an aerospace background. When you look at the intrinsic definition as primarily the points raised by Sylvester, strength is indeed normally defined as a parameter that is controlled by measured under uniform stress, that should not be size dependent, all under very strict conditions. But I think those strict conditions, you cannot apply these to composites. The size dependency is something that you cannot you cannot take away in composites. But that definition originally was probably done for metals, where size dependency is much less of an issue. So applying the strict definition, I think, is a bit senseless in the case of composites. But Sylvester did highlight an interesting way of looking at that is through looking at a Weibull distribution for size scaling and then taking the Weibull distribution parameters as the material parameters. That's one way of avoiding that effect.
I think was a very interesting point. And I think another thing which Sylvester's talk made me think about, though, is when we quote values, strength values, we don't really want them tied up with a model, because unless everybody agrees with that model, then it's not going to work. So I think that's another thing to think about. Even if we think that we need to take account of the volume, maybe what we should do is specify some standard sizes to test rather than try to extrapolate based on Weibull or any other theory.
Yeah, I agree. And I think it's also important when you want to use then models to interpret what would happen if you have a different width or a different thickness. That's in principle a really good way of doing it, but in practice, I'm not sure that works, because then you would have to have a lot of confidence in those modeling tools. And for example, for size scaling of unidirectional composite strength, I don't think we have that faith in the models at the moment.
Can I add to this?
Sure.
So I think that one of the issues is that if you make standardized test sample, that probably not fail in a correct matter. And the issue is, then of course, for a design point of view, then it's okay, because then you have conservative values normally, and that can be maybe not so conservative, but still, if you compare materials and want to improve the composites, then it's an issue. And I think the problem is to get, you could say, I don't think you can come up with a test sample geometry which are working for all materials, and especially also when we begin to talk about protrusive profiles, which are something which are really idealized high volume fraction materials, where you cannot make thin laminates. You have maybe a 5 millimeter laminate. How to test that and link that to the fiber strengths could be a good way, but then you may rely on maybe a curtain model which are made for ceramic composites, which may not describe the failure mechanism, and you cannot really see the failure mechanism. So and you have a very length scale dependent fiber failure. So how to get this correct strength just of a UD laminate? I'm not really sure about how to do that.
It's a challenge, that's for sure. There's a question here from Xiaodong Xu talking about the effect of stress singularities, and that strength is perhaps less valid characteristic, rather fracture toughness is more relevant, and a suggestion that really we should have another workshop on toughness. I think that's a good point. There's toughness as well as strength, and that's also important.
Michael, could I make a comment?
Yes, please do.
Okay, just a couple of things in response to a lot of very thoughtful comments made before. Sylvester said, strength of coffee is strong or weak, markets are strong or weak. That's all good. We are in the world of mechanics. Our language is mechanics. And when we say strength, we imply without any doubt that we are talking about one stress with maximum value corresponding to some critical behavior. If that's not what we say, then we don't belong in the community of engineers, because our language is mechanics. In mechanics, we don't have a single stress component, we have 6. And even though we apply a load and determine something that we call nominal stress and take its reference value at some critical behavior as strength, it is wrong, because that's not what is happening. It happens in metals, as I said before. So it's a triaxial stress state that is driving the failure mechanisms, whether you take a unidirectional or you take any complex architecture, it is the same situation. failures occurring by local driving forces in terms of the local stress states. And they have 6 components generally, even though we define something of a nominal strength, which should not be. I hope someday we will stop using that word strength and call something else as a reference, whatever, reference load, critical load, whatever. So that's one comment. The other is with respect to what Tony said. And we are both in aerospace engineering departments, and we face the same challenges coming from the industry. Industry needs to certify their structure. And they have this pyramid where you start with coupon testing, go to subcomponent testing, component testing, and so on. Again, all of that conceptual structure has been developed by metal thinking people in the time when metals were the materials for aircraft. Today, that's not the case. I think that has limited our ability to think rationally and see whether you can actually take information from the coupon level to a higher scale level, like what Ola was saying. Why don't you start from the top and see how a structure fades? Yeah, sure, we can start from the top and do structure analysis and go to hotspots, but at the end, it's the material that triggers the failure. And it does it in general triaxial stress state with driving forces, stress singularities, stress concentration, and things of that nature. So unless we connect ourselves to what is physically happening, we'll be going around in circles and not coming out of it. Sorry.
Okay, thank you. Endel Yave's got his hand up. Would you like to speak, Endel?
Sorry.
Yeah, Endel, you're muted.
Yeah, a word on top of what Ramesh has said. So do you mean, let's say, there are inevitably always 6 stress components in any failure case, and there's this nominal, let's say, primary stress corresponding to the strength we are calling for. Is that what we're trying to say? In that context, then, do we need to give, let's say, more information on other stress states in even a uniaxial testing conditions?
No. The nominal stress is not a stress. It cannot be transformed. It doesn't have coordinate transformation. It does not have principal stresses or anything. It is not a quantity that, for mechanics, Cauchy stress, it is not qualified as a Cauchy stress. Nominal stress is something that we have created for convenience. And it was okay for metals because that is the same stress that is causing failure, assuming it's homogeneous material with no complications at the microstructural level. But in composites, or in generally in any heterogeneous system, the connection between what you apply, you call remote stress, and the local stress, there is no connection from stress to stress. So one is the reference, the other is what is happening. If I just change the fiber architecture a little bit, with the same nominal stress, I have a totally different triaxial stress state, and therefore trigger totally different failure mechanisms.
Okay, I see what you mean. Yeah, thank you.
I just ask, Endel had his hand up earlier. Did you want to ask something, Endel? You're on mute at the moment. You should be able to unmute.
Yes, sorry about that. This unmuting. Okay, very good. So I am, of course, on the receiving end of this discussion in the sense that I feel myself more as a consumer of these definitions than someone who contributes to them, because I'm involved in predictions. And what I'm looking at right now on my screen is a set of input values, which it's a pretty typical one, which goes into the prediction of, we've worked quite a bit on different composite structures here, and there are dozens and dozens of these input parameters. They, of course, include all the orthotropic properties. They include all of the typical ply level strength values. They include fracture toughness values. They include our normal fracture toughness values, so to say, the ones mode 1, mode 2, which we measure in our TCB and ENF specimens. They also include some less traditional fracture toughness values, such as the fiber direction fracture toughness. And there are situations when these are those elusive parameters which actually affect quite significantly the predictions which we make on a structural level. And I can go in other type of these parameters. For instance, in the compression failure, again, there are some concepts which one has to employ, such as the retention of compression strengths after, or retention of the resistance in compression direction in the normal direction after the compression strengths. And the reason I'm bringing this up is that I think that the definition, the definition of the strength values in the way we look here, we looked here in terms of the unidirectional fiber strengths is certainly very important, and there is quite a bit of work to do. But I would also think that maybe we want to concentrate on some less defined strength concepts altogether. You know, such that I mentioned, which are very important for making structural predictions. And I have some other things to say. I just don't want to, you know, muddy the water too much.
Number of points there. Yes. Well, thank you. Marino, did you want to raise something? Did you want to raise something from the chat? You're on mute at the moment.
Okay, thanks. Actually, I have a question from the chat. Let me recover it. It's from Sergei Kravchenko. Could you please elaborate more why you think that it would be best not to use the terms strength and failure stress interchangeably? Do they not both quantify the load carrying capacity of a test article in terms of the far field applied loading? That's the question for the panel.
Well, I guess since I raised that, perhaps I'll take that initially. I was...
yeah, actually, that was the point, but I was not interrupting the flow of presentation.
Sure, no.
At the early beginning of the meeting.
Yeah, I made that distinction. I hoped it might be helpful because I think applied failure stress to a number of different conditions. And I tried to make that distinction in our paper with, because I think that perhaps we consider strength as a fundamental material property, if we still believe that there is such a thing as a fundamental material strength for a composite. I mean, that's one of the things that's been debated. Even at a small scale, a composite is really a structure. So we could throw our hands up and say, well, it's all a structure and we don't have a material strength. I was trying to see whether we could hold on to some concept of a material strength, and then suggested that we consider a failure stress in situations where failure depends on other things other than just the fundamental material strength. So in a laminate, as Federico also showed in his case, it depends on a number of other factors, not just the intrinsic material strength. So I tried to make that distinction to really separate those two. Federico, do you want to say anything about that? You're muted.
You are muted, Federico.
Yes. No, I absolutely agree. We have discussed this perfectly. So the difference in between both. But the difference is also that when talk about the strength, probably you have the possibility to define it properly. When we talk about failure at the stress or allowable for a designer, the definition is not so clear. And it depends on what you think the designer expects from you. The question is also that I forgot to mention this point, and I'll let you this possibility to do it now, that when you test at the whole component, probably, Ole mentioned this, probably the strength of the material as itself is not involved in the failure. So most of the failure came from the joining procedure, from properties of the interface between different parts, between the skin and the stiffener, and are properties different from those we generally call strength, and come more associated with the concept of toughness, because I have discussed many times with Ramesh, energy is the main magnitude that control the behavior of a structure at all kind of levels. It doesn't matter where you are. I have maintained many conversations with people that design structure in the aeronautical industry. And when I told them that I'm working at micromechanical level, they say, this is very interesting for a lecture. But for me, I'm not interested in this. And when I explained them, no, look, I'm trying to understanding the behavior, the mechanism of failure that happen at micromechanical level to allow me to give you advices of how to design something to delay the appearance of damage or to make something with more able to carry higher loads. That's all.
Can I jump in?
Paul Bromstead has his hand up. Perhaps, Paul, would you like to make a comment or question?
I'd like to make a... Hello, all of you. Very nice to meet you again for a long time. It's very interesting to follow the discussion, and I was, of course, this has been one of the topics I've been working with for all my years. I wonder if you think of that. Many years ago, we were thinking of making a virtual test lab. Now we have virtual meetings. But making a virtual test lab where you analyze your test setup and put the right basic inputs or the needed basic inputs into your tests, and then analyze the test and see how they respond. Then you can, in that way, detect or follow what are the importance features to put into also other models of that.
Tony, did you want to make a comment?
Yes, I wanted to make a comment because the discussion is very, very interesting. And I think we are, the way I see it, I think we are zooming in on something that can tie in what Ramesh said, what Michael, you said, what Federico said, and what Ole has raised. So I in the chat box, in the Q&A, is separate from the chat. In the Q&A, Ole typed up his initial comments, which were that many times structural failure, and Federico alluded to that as well, that many times structural failure occurs by a structural level mechanism, and then the material aspects come in only much later. And that's why Federico has these comments from outside engineers saying, you can do that, it's an academic problem, it's great. But here's the catch. And I think Ramesh alluded to that very nicely. And here's what I think is happening, right? In the metals world, the distinction and the relationship between the applied loads and what's happening inside the structure at the point where things happen, the connection is rather trivial because it's only one mechanism. But in a composite, if you change one ply in your laminate, you have changed the local stress state of all the layers at that point where something is happening, even though macroscopically you have the same deformation and stress state. So if I take a structure, a big component, and I want to apply compression load, it will buckle, go into the post-buckling regime. And let's say I take 3 different layouts. All of them have the same macroscopic stiffnesses. So now my macroscopic state is identical in all 3. However, when I go locally to look at what's happening locally, they're going to be different. And so the failure mode is going to be different for these 3 structures, even though macroscopically, the triggering event was post-buckling and loading into the post-buckle state. So what I'm trying to say here is that the challenge for us is a lot more, because we have to do 2 things. We have to understand the local mechanisms, which Federico rightly said he should be studying, right? At the micromechanical level, he should be doing what he's doing and do more of it. But our work is not complete until we connect what's happening at the micro scale, the triaxial stress states that Ramesh is talking, to the macroscopic load level. And that's a challenge, which brings me to the next point, which means that just defining strength is not sufficient. We need to show the connection of that strength to the model and to the macroscopic state, which is an extra element that metals people never had to do. Metal design doesn't have to do that, right? But we have to do that because we have this added flexibility of changing our layouts, right? So we can design quasi-isotropic laminates whose stacking, whose layup is different. You take it to the lab, you put it under compression, a stiffened panel, you can get all three panels to behave almost identical. Until it starts to fail, then you'll see that the three panels fail differently. And why? Because locally, you have altered the stress state by changing your layups, by changing your geometric details locally. And that's where I think what Federico said and what Sylvester said earlier, it has to come in. Material must come in there, because if you don't have a good grasp, a good model at the local microstructural level, there's no hope to connect and unify the response of those three panels. So imagine you're an engineer at Boeing, at the Boeing company, and you have three panels, you're testing them, and you measure your macroscopic response, and they look similar. They look similar, but then it collapses and fails. And then when they go and look at the details, they find that one had huge delaminations, the other failed rather locally, a third one failed differently. And now they start looking a little bit deeper and they realize, wait a minute, I changed my stacking sequences. I have macroscopic quasi-isotropy, but locally I've changed things, right? And so those changes, if we want to, as a community, build confidence with the airframers and the broader community, we need to tie those two. We need to tie the nominal or macroscopic applied loads to the microscopic mechanisms in a convincing manner, so that we all agree that, wow, this is the correct way to do it, and we are getting consistent results. I think I
agree. And I agree, that relates to the example you gave in your talk about the angle ply laminates with the zeros. And clearly, you cannot just take a unidirectional strength and predict the failure of a laminate. But so I think there's two things. First of all, here, we were trying to address the basics, because I think we can't even necessarily agree on the unidirectional strength, let alone the laminates. So I think we've got to start somewhere, and start with the UD. And if we try and agree on how we can define and measure the strength of the UD, then we can start building on a firmer foundation in terms of trying to predict what happens in a laminate, which is far more complex, as you and others have pointed out. So, Young, do you want to make a comment or ask a question?
Sure. As Tony mentioned, and also the Oleg mentioned, that if you're going to look at the failure at the structural level, then that's going to be different from the failure at the laminar level, because of more complication of the structural level. So in that case, I think we have to really use the the multi-scale technique, so that we can link different length scale, etc. And eventually, I believe that the failure have to be looked at the constituent material level, because that's going to be the foundation of the the basic failure, either fiber failure, matrix failure, or interface failure. So whatever happening at the local level, that is going to affect that the stress strain at those constituent material level. So that is going to be a little more easier to apply up to the structural level using multi-scale technique. And as far as the size effect, that even you got a small size, large size, failure is going to initiate at one point and then propagate into the rest of section. But the important thing is, if you have a different size, then the defect is going to be different. If you have a larger specimen, larger size, then you have a better chance of the more defect, and then larger size avoid those kind of the micro defect or misalignment. There are more effects, so that is going to also affect the strength of the composite too. So somebody is going to use in the industry for those strengths for, for design. Then they never use the small scale, coupon size for, structural application. So in that aspect, if you're going to define the strengths, even the, laminar level, then we have to consider that, considering all those kind of possible defect in the specimen. And then because the nature is going to be stochastic, as people mentioned, so we can provide that with, for example, 95%, 99% of confidence level based on that, considering those size effect and that's going to be the strengths we are going to provide. Then I believe the engineer can use it with some kind of confidence of that, those value in actual design of their or analysis of their composite structure.
Sylvester, Soraya, do you have any comments or questions to raise? Or Frederic?
Yes, I have a question for all of you. We have talked a lot about the stress at failure or the strengths, but finally we don't talk about the strain at failure. And I just would want to put the strain, because today the strain is a quantity that we can measure, and with digital image correlation, we are able to measure the multi-axiality of the strain applying to structures, and you can find now some works in which you're able to control the loadings that you introduce in order to obtain the strain that you want at the end. And today we have talked a lot about the stress and the strengths. What about the strain for the onset of failure? Because it is very convenient to measure. We have not talked about the stress versus the strain and how you want to deal with that, because lots of industrial also use, for instance, a maximum strain criterion. Could you give us your opinion about that, stress versus strain, and the advantages and limitation of both of quantities? I'm interested about your opinion on that.
Well, let me just say something first and then pass on. I think it's a really good point. And as you say, strain can be measured directly. And in a simple unidirectional test, then I think strain is a very good measure. And Jentel showed the specimens with tabs built in. Actually, I don't like to think of them as tabs, but glass on the surface. And that's very, very good for measuring strain. But as he pointed out, you can't measure the stress from that without back calculating it. When you have multi-axial tests, such as the one you showed for the tension test, where you're putting multi-axial stresses into those 90-degree plies, then you've got strains in different directions. So you've got stresses in different directions, and therefore it's a bit more complicated, as you know, to derive the stress from that test. But I think it's a really good point. I think strain is perhaps a better starting point for some of these fundamentals than stress, but at the end of the day, what we really want is stress. Jentel, do you want to say something about that?
Yeah, I want to comment that I kind of agree with Frederic in the sense that failure strain, I think in a lot of ways is a lot easier to handle, especially when we're talking about, for example, what you see reported in data sheets for carbon fibers. If you want to compare the carbon fibers to each other, they do this based on UD composites, and they report it as a fiber failure strain and a fiber strength, but it's all back calculated. If you get a strength for a fiber based on a UD composite, that depends on the fiber volume fraction, and failure strain doesn't have that problem. So that's another reason I think why failure strain tends to be much better. Imagine if I had reported the values in my presentation all based on strength, and there were some fiber volume fraction variations between the different panels that we manufactured, then you don't know where the differences are coming from, whether it's from the NTAP design or the testing conditions, or from intrinsic differences in fiber volume fraction.
So Jentel, if I can just follow up on that and ask you, when you presented the strains, you compared them against the reference strain. Where did that value come from?
Yeah, well, in principle, the answer is we don't really know, but in practice, most of these datasheet values are based on impregnated bundle tests. So they impregnate, if it's a 12K carbon toe, they impregnate that toe, and they do a UD tensile test essentially, but on a much smaller scale. So there are size scaling effects, and that's also the question that Lars asked in the chat box. In principle, they are, let's say, for a 12 to 24K carbon toe, they are 10 to 20 times smaller than what we typically test in a UD tensile test on a regular composite. So there are size scaling effects there. That's why I think the datasheet value is a little bit higher than what we measured.
Good point. Other questions, comments?
Yes, Michael?
Oh.
Sorry. Okay. Sorry, I just want to comment on what Frederick mentioned about the failure strain. I think it makes a lot more sense, even than strength or stress, for some failure or deformation mode where there show lots of nonlinearity or plasticity. For example, in plane shear, the plastic stress may get even plateaued before failure. Then it's much easier to use a failure strain than a failure stress in that scenario. Yeah, that's it.
Even one thing of the advantage of using a failure strain compared to stress is going to be in terms of modeling, because if you're going to model the progress failure, then as the failure progress, then it's going to increase. But once you have a failure, then stress decreases, because at the point that the component cannot carry the load anymore. Then you have to kind of bookkeeping of those kind of the progress of failure in terms of stress, but in terms of strain, then it's naturally strain is keep increasing, so you don't have to worry about that one. So I believe that at least in terms of modeling perspective, then strain is easier than stress in dealing with those kind of progress damage and eventually final damage.
There's a question here from Paul Weaver, who says that he's listened with interest. The only point for defining a strength is for design purposes. Nothing yet in this debate has convinced me to change from using max laminate strain allowables. It is simple, independent of stiffness, measurable. Can we raise strain allowables to 10,000 microstrain? Well, there's a lot in that question. I don't know who would like to take that one. And I guess it comes back to this business about allowables versus strength. I would actually take issue and say I am actually interested from a fundamental materials point of view in knowing what that ultimate strength is. And even if it's not going to be usable for design, because I think that's the starting point to build a firm foundation on. So we can measure, we can come up with an allowable strain or stress, but that has to take account of a whole lot of factors. And from a design point of view, you just got to make sure you're conservative. But from a fundamental point of view, as I was saying in my talk, you want to know what the real value is. If you've got a knockdown, BAE Systems didn't like some of the early tensile test standards which were developed in the UK because they produced values which were too high. Now, to me, you can't argue that a too high value is wrong. It's just that, that it was unrepresentative of what they achieved in structures. And probably the reason for that was because they had different factors which were knocking it down in their case compared to the lab tests. So what we need is, in my opinion, is a firm foundation to understand what the real ultimate strength is and what are the factors which knock it down, so we can take those into account in a rational way in establishing design allowables. I've probably said too much about that. I really wanted to open that to the panel to see if anybody else wanted to comment on that question.
Yeah, Michael, I completely agree with your point. I think in a lot of industries, if they talk about design allowables, I would presume in most cases they're defined on the ultimate strength time divided by a certain safety factor. And then you still need to know what the ultimate strength or the tensile strength is in order to know what the design allowable is. Now, that might not be true for all industries, but I think in a lot of cases that will be true.
In many cases, it's based on compression after impact, for example, which is a very pragmatic and important thing, but it's different from an ultimate strength. There's another question here from Ali Aravand. In agreement with Frederic, experimental data show far more uniformity in strain rather than stress, especially considering the fact that it's been shown that the failure envelopes of individual plies aren't affected by each other. Hence, superposition would be possible. This approach eventually results in envelopes in principal strain space, which could be more easily related to experimental measurements. I guess that's more of a comment than a question. Are there any other responses or questions from the
Yeah, Michael.
Michael, I have a question.
Ramesh, sorry, Marino.
Faisal Yawaland, I suppose the whole discussion is about terminology and using word strength, more precisely. The issue of having words with complex or interpretation is not an issue only for one word or only to composite material. As said by Wittgenstein, I think, if you wanted to speak fully precisely, we should not open our mouth. I think Michael and Federico are suggesting that word strength is not enough simple and precise. We should remember that language is a tool to communicate between members of a community. As far as both sides of the communication members of that community understand to a good extent what the word is referring to, then we can use that word. Personally, I agree that personally, I agree with the confusion the word strength causes. Like many others, prefer using stress at X event. In my opinion, if someone reports the strength of a coil laminate is X MPa, then I'm not sure exactly what has happened and how they have reported that value. Also, we should also remember that language is quite dynamic. That's the comment I found in the chat.
Okay, thank you, Maria. Thank you, Mason, for that. We're coming towards the end of our time. I'd perhaps like to draw it together to think about what the conclusions and next steps might be. Clearly, we've debated an awful lot of things here, and it's all extremely complex, and it's perhaps quite hard to see how we can make progress. But in our paper, Frederic and I had a few suggestions which we put forward, and I'd like to put that, just use that as a starting point and see what you think about these and whether you've got ideas, suggestions for other things that we could or should do. So one of the points I was making was that, that there's an awful lot of work which has been done on testing, and lots of papers are published, but we're not so good at synthesizing, taking all those results and saying, well, what do they mean and which are the methods we should be using? Okay, there's quite a lot of work done in the standards committees, but I still think there's a need for a lot more work to really, rather than creating new tests, looking at all the work that's been done and trying to reach some conclusions from that. I think also there's the whole question about what affects strength. So some things we put in our paper, some things other people have mentioned this afternoon, but I think we need to get to a consensus about, well, what actually does affect strength, and therefore come up with, to answer that question, what further research is needed to be able to take these values and use them to predict laminate and structural failure from basic material strengths. That's the holy grail. That's what Tony and others were talking about, and we're quite a long way from that. But I think what would be helpful was to try, rather than everybody doing their own little bit of work, if we can try and come together and reach a consensus on what needs to be done, and then collaboratively plan some programs to address some of those things. And what we suggested was an initial step to organize a series of workshops looking at the primary failure mechanisms, starting perhaps with fiber direction tension, but then also looking at compression, shear, and transverse as well, and looking at what's been done, what's understood, what problems are known, and what solutions are known, and see if we can move forward by having a more detailed discussion about some of those individual different failure mechanisms. So those were some of the suggestions in the paper. I'd like to hear from initially members from the panel. What do you think about that? And have you got other ideas to suggest of what we should do to try and make some progress? Because it's easy to see that this is a very complex problem, and we almost throw up our hands, but I'd like to see us move forward. So, comments, questions?
Could I maybe start, Michael?
Yes, please, Ramesh.
Yeah, I would take your last bullet as sort of something to move with, because what we have done today is free-flowing brainstorming type of discussion. So if we take next 2 or 3 or maybe more workshops, focus them on one specific sub-issue,
yeah,
and do the following, which connects with the other bullets. You know, in academia, we understand situations in very nuanced way, and therefore we have difficulty agreeing because of nuances. But we have to keep our eye on the eyeball on the industry, but they are the ones that are going to be using it. Now, I'm old enough to remember the time, just before, many years before Composites, in the methods where we were discussing strength versus fracture toughness. And the industry people were so adamant about the fracture toughness, they say it's nonsense because stress singularity doesn't exist. You know, after decades of struggling with the industry, today it's common practice for them to use fracture toughness. And we are educating engineers who are working in the industry. So we had to do this dual approach. One, to train our young researchers in properly using mechanics concepts, communicating with the language that is rigorous, and then at the same time finding a way to connect with the industry so that they don't think that we are just playing around with things. You know, these are serious matters. What happens locally in terms of failure versus what we measure in a laboratory. I mean, this can take even another 5 years or more to communicate to young researchers. If the industry is going to take even longer. So I support the idea of organizing next series of workshops with those two purposes in mind.
Thank you. Other comments or suggestions?
Yeah, I want to support the idea that you proposed, Michael, and that Ramesh also seems to agree with. I think it's difficult to agree or to reach a strong conclusion based on what we've discussed now, because it probably covers too many topics at the same time. And I think this is good in preparation for more dedicated workshops on specific topics. And I think the tensile and compressive strength measurement are very important topics that I think a lot of people in here are quite interested in.
Thank you. Marino, did you want to say anything?
Well, actually, your conclusion summarized. Sorry, I know I'm speaking. I'm just checking them. Mic. Summarize what we started discussing some ago when we planned the event, and what I said before. Actually, there is the need to be a bit more focused on the level, and then maybe we can find a, I would say, larger agreement on even on the definitions, because if we mix up too many scales, I would say it's really difficult to be clear in what we have in mind. At the same time, if we can start from, let's say, testing the unidirectional lamina under tensile loading, then I would say the community, which is not that large, will even shrink. And then maybe we can go more on the point of which is the meaning of failure, as Ramesh pointed out, because I mean, we can make millions of examples. If you test a UD lamina, you can have a tab failure. You have to define how the sample is where you have failure. And still, you have to decide which is the mechanism that brings you to failure. Even at a very simple test, which is pulling a 0-degree specimen. Something that was stressed before by Tony, if I remember well, was the point of misalignment. In a tensile test of UD, a 0-degree ply, few degrees make really the difference, and you can measure something which is completely different. But even at that point, I would say that I would try to decouple the let's say experimental issues, because we can really make a huge list of things, and I believe that all of us, depending on the previous experience, background, can write a book on the problem in testing composites. So,
okay, thank you, Marino. I think that's good. Seems to be quite some consensus for progressing with these workshops. We're nearly out of time, so just to finish off, just like to pick up one comment from Bent Sorensen here, who says, I think we should use strength as a material property, i.e. size independent. Scale effects is central. I think that's a good point. And I'd like to ask Federico, before we close, have you got any final comments or remarks?
Yes, on my side, in accordance with the conversation I have had with Michael, we understand this is not the end of our task. This is the
Start.
starting point of our task. Now we are going to spend a couple of weeks or 3 or revising what all of you have said, and we promise to go back to this with some proposal, creating special groups to the identified question that concern most of us. And I hope you will continue to be involved in this, let's say, project.
Thank you very much, Federico. So thank you to all our panelists who've really made this a very interesting discussion this afternoon. Thank you especially to Federico for helping me with this. And Ramesh, thank you also for your support. And thank you to our delegates for attending. We will make the presentations available, and there should be a recording of this available. So we will let you know about that. And thank you to everybody, and have a good weekend.
Thank you.
Bye.
Bye.
Thank you.
Bye.